And now, scientists at the National Ignition Facility in California are actually trying to recreate that solar process here on Earth. Fusion forces two hydrogen atoms to merge into a single helium atom. Pound for pound, it's the most energetic reaction in the cosmos. And that's what his facility would like to reproduce.
We crash them together, and what happens is we turn mass into energy, just like Einstein told us.
To do this, Ed's team focuses 192 of the world's most powerful laser beams onto a BB-sized capsule containing hydrogen atoms. This fuses them into helium atoms and releases a 100 million degree pulse of energy. The goal is to create a sustained fusion reaction, but right now it lasts only a billionth of a second. Stars create helium throughout their long lives, but in their old age, they run low on hydrogen and begin to fuse helium, creating larger and larger elements.
And you'll start walking up the periodic table, making more and more elements. First you made helium, then you'll make lithium and beryllium and boron. And you can do this all the way up to iron.
By the time it's fusing iron, a star is in its death throes. It begins to collapse, and if it's massive enough, that collapse leads to a powerful explosion called a supernova. In that intense flash, the supernova creates elements heavier than iron, launching them all into the cosmos, creating the raw materials of planets and of life. And now we're using those raw materials to shape our civilization with elements like silicon, 14 protons, 14 electrons, the second most abundant element in the Earth's rocky crust. A member of one of the smallest neighborhoods on the table, the semiconductors. When most people think of silicon, they think of computer chips and the information age, but its most familiar form is actually in this. For more than 5,000 years, silicon glass has brought light and beauty to our lives. Today, scientists are re-engineering this ancient material, atom by atom, here at Corning in upstate New York.
You know, David, this place looks and sounds like a blacksmith shop, but actually it's a scientific laboratory.
They're fiddling around with various combinations of elements,
That's
seeing
right.
what kind of glass comes out.
They tell me it all starts with ordinary sand, which is made of a combination of silicon and oxygen. The glassmakers have learned how to precisely place minute amounts of metal atoms, like sodium, potassium, and aluminum, among the silicon atoms. The result is hard, yet flexible, and scratch resistant.
No!
But is it really glass?
So you maintain that this is not in fact plastic, that this is actually glass.
But yet very strong. Within reason. There's no such thing as an unbreakable glass. It is a glass. It is a glass. So there are limits.
But perhaps the real shocker is that these 15 elements were so long misunderstood, their identities masked by their identical outer electron shells. But those aren't the only atoms hiding from view. Scientists now know that most elements come in more than one version. The different versions are called isotopes. Consider carbon, the backbone of life. It has 3 natural isotopes, or versions. Each has 6 protons and 6 electrons. That's what makes them all carbon. The difference between them is the number of neutrons in the nucleus. Neutrons are electrically neutral particles that act as glue to hold atoms together. What we think of as normal carbon is called carbon-12, 6 protons plus 6 neutrons. But about 1% of carbon atoms have an extra neutron, giving them 7. They're called carbon-13. And about 1 in a million have 8 neutrons. That's carbon-14. And that rare version of carbon has proven to be a crucial tool for unlocking the past. Several times a year, scientist Scott Stein travels to the shores of Mono Lake near Yosemite National Park.
This then is Mono Lake.
Mono Lake, yeah, right here at the foot of the Sierra Nevada.
He's studying the long history of droughts in California, trying to determine how frequently they occur and how long they last. Over the millennia, the water level has risen and fallen as the area has cycled between wet periods and dry times.
Oh, so that sandy area should be the level?
During times when the climate was dry, Mono Lake dropped down, exposed the shorelands, and allowed trees and shrubs to grow.
When the dry periods ended and the water level rose, the trees drowned, marking the end of the droughts. Since then, the remains of those trees have been well preserved by the arid climate.
These droughts were long persistent.
To determine how long ago these droughts occurred, Scott is using carbon-14 to date the trees. Unlike the other natural isotopes of carbon, carbon-14 is unstable. Over time, its atoms begin to deteriorate. One of its neutrons turns into a proton and spits out an electron. Now with 7 protons instead of 6, it's turned into nitrogen. That process is called radioactive decay, and scientists know exactly how long it will take for half of any amount of carbon-14 to decay away. Scientists call that time its half-life.
Intact wood is a very good material to date. It retains the carbon from when that material died, and we're able to extract it, purify it, and get a really good material for dating.
Tom needs only a small amount of wood. Even this tiny sample is overkill. A lab technician cleans it and reduces it to a fine powder.
Oh man, this huge thing? This is your Carbon Dater-Matic 3000?
The actual counting of the atoms takes place here, in the carbon dating accelerator.
We have our 1 milligram of carbon from the wood chip sample basically in that hole.
In that tiny little hole?
That's where the 1 milligram of carbon is from that sample.
Not a lot of wood chips.
And we put about 64 of these holders in one of these wheels.
The accelerator applies a powerful electric charge to the atoms, basically lightning, giving them the speed and energy they need to hit a detector with enough force to be counted.
The ratio of the carbon-14 ions to the amount of carbon-12 in the sample tells us how old the sample is.
The fewer the carbon-14s, the older it is?
Yes.
Carbon-14 has helped open up deep insights into the past, but it's just one of hundreds of radioactive isotopes, that is, elements that decay. In fact, at the bottom of the periodic table, beginning with number 84, polonium, all of the elements and their isotopes are radioactive, including the element that stands for both the promise and the peril of radioactivity, uranium. 92 protons, 92 electrons, and 146 neutrons. Before the nuclear age, uranium was thought to be the end of the periodic table. But in the last 70 years, scientists have left nature behind and created 26 new elements. The age of man-made atoms began in the first half of the 20th century, when researchers began bombarding elements with neutrons. Sometimes the neutron is simply absorbed, creating a new isotope. But sometimes the nucleus can't take the punishment. It becomes unstable and splits into 2 smaller atoms in a powerful reaction called fission that releases large amounts of energy. To learn more, I've come to the Nuclear Museum in Albuquerque, New Mexico.
Okay, now to the naked eye, this looks exactly like a nuclear reactor.
The similarities are the mousetraps are uranium atoms, and the white ping pong balls are neutrons, which you use one to start a chain reaction.
In a reactor, 1 neutron splits a uranium atom, which releases energy and 2 or 3 more neutrons, which in turn split more atoms, releasing more neutrons, and so on, causing a chain reaction.
So you get more and more neutrons, and thus the chain reaction keeps going.
All right, ladies and jelly spoons, here goes the orange ping pong ball. This evening's role, you'll be portraying the neutron. All right, I just drop it in here.
You just drop it in right there, and we'll start the chain reaction.
Incoming neutron! I'm sorry, Matt. The camera wasn't rolling. Can you set that up again?
From a single neutron, an escalating response. Our mousetrap reactor doesn't have many atoms, so the reaction dies quickly. But pack enough fissionable uranium atoms closely enough together, and the whole thing can get out of hand pretty fast. And sometimes that's the point. This museum has the world's largest public collection of artifacts that chronicle the dark side of nuclear energy. In 1945, the US developed 2 atomic weapons. Both were used against Japan. The first was fueled by an isotope called uranium-235. That bomb was called Little Boy. The military made only one uranium bomb, because separating rare U-235 from the more common U-238, which doesn't work in fission reactions, is a very difficult process. So for the second bomb, called Fat Man, they used an entirely different element, plutonium. 94 protons, 94 electrons, and 150 neutrons. Plutonium was the first man-made element. It was first created as an accidental byproduct in the first nuclear reactors, but no one knew it until plutonium was identified in 1940 by chemist Glenn Seaborg when he bombarded uranium atoms with protons and neutrons until some of them stuck. Over his long career, Seaborg went on to isolate or create 9 more man-made elements, including americium, which is in minute quantities in the smoke alarms in our homes. He pushed the end of the periodic table all the way to element 106, which is called Seaborgium in his honor. Since the end of the Cold War, Ken's goal has been to expand the periodic table. He's teamed up with a Russian lab, and together they've succeeded in creating 6 new elements in this cyclotron. But there's a hitch. They've only made a few atoms of each, and they're all so unstable, they decay away almost as soon as they come into existence.
With all due respect, none of the 6 elements that you've discovered are actually in the world right now.
That's correct.
So do they count?
Doesn't sound like much, but for a chemist, a 10-second activity actually allows you to do something with it, but it isn't enough that you can put it in a bottle and put it on the mantelpiece and admire it the next day.
Still, Ken has high hopes for the future. He believes that somewhere beyond today's largest man-made elements, scientists will find an island of stability on the periodic table, where some super large atoms will be both stable and useful, perhaps satisfying the needs of our future civilization. It's amazing to think that something as complex as the physical universe can be put on a single chart. And from about 90 basic elements, man and nature have teamed up to create the incredible variety of stuff in our lives. And the story is far from over. As scientists continue to hunt the secrets of the elements, what new understanding and technologies will follow can only be imagined.